Let's quickly go ahead and focus our attention towards output protection circuits now. Let's see what's going to happen at the output. See, output circuits technically, let's say this is my output circuit, right? This is my CMOS circuit. This is my output pad. So my CMOS circuit should technically be able to drive the pad. The CMOS circuit at the output needs to drive the pad. Pad will have its own capacitance along with the external load. External load means the circuit which it is connected to. So the CMOS circuit should ensure that it is able to drive this load. That means it should be able to drive a huge capacitance, right? So output circuit would have to drive its load. Let's say an example, this is an inverter, this is an inverter. The output capacitance of its own plus the input capacitance of the external guy, right? And there is a pad in between. So this inverter should be technically able to drive this huge load. Are you all with me? In case you have not followed, I'll quickly make you understand. So let's say this is one of the inverters. There is a pad and it is being driving some other circuit externally, correct? So this inverter technically has its own internal capacitance which it has to drive plus the pad capacitance, and it has to also drive the circuit. So all this together, what it has to drive is a huge capacitance at its load. So what's going to happen is the time delay will reduce considerably, because we know that time is nothing but, if you're considering charging time, it's nothing but tau into RCL. Discharging time is nothing but R is nothing but the intrinsic resistance of the MOS, R into CL. This is RP and this is RN. Now what will happen is the load is huge. So when the load is huge, we know that the delay will be very high. So is there any way to reduce the delay? Absolutely yes. If we reduce R, then my delay is reduced. So how do we reduce R? We know that I is proportional to W by L. That means R is inversely proportional to W by L. We have seen the equation of ID, right? ID equal to mu n COX W by L. So I is directly proportional to W by L, which means R is inversely proportional. So in order to reduce R, what we have to do is increase W by L. So increase W by L. Now what's going to happen is, if you increase W by L, say you have increased W by L of this also, you have increased W by L of this also. Now the input capacitance of this inverter, which is given as CG, is equal to COX W into L. So when you increase W, your CG increases or the gate capacitance increases. So on your MOS IC, another inverter or another gate would be driving this gate, which in turn will become slow. So are you understanding what's happening here? So what we do is, rather than increasing the W by L, we don't make one inverter of a huge size drive a load, but we connect a driver chain. What do I mean by driver chain is, I'll quickly explain. So we don't have a huge inverter driving one load. This entire load would be driven by 3 inverters, and each of them, suppose say this has W by L X, this will have something plus of X, this will have something plus of X plus plus. So each one of them is going on increasing in its size. Now what's going to happen is, X has to drive only X plus, so it will not get very slow. X plus only has to drive X double plus, so it will still not get very slow, compared to this guy which was X triple plus, suppose, or something like that, and this previous guy had to drive X triple plus, so this would have gone tremendously slow. Here we are distributing the capacitance in such a way that it's not heavy pressure on one huge sized inverter. So this is nothing but the concept of driver chains which we use at the output, correct? So in summary, in output, what we can understand is, output needs to drive a huge load, external load or external circuits which are connected. When this huge loads needs to be driven, we saw that with tau, the delay would reduce, correct? Because tau is equal to R into C. Now, if we want to reduce our delay, we need to reduce our R, which is the intrinsic R of the MOSFET. If we have to reduce our R, we know that R is inversely proportional to W by L, so I need to increase my W by L. If I increase my W by L, its gate capacitance will increase because W has increased, correct? When I say increase my W by L, I means that L is saying the same, I'm just increasing my W, okay? So don't get confused. So when I increase my W, my gate capacitance is increasing, which means the guy which was driving my gate will become slower. So we don't want that to happen. So we don't want a single inverter or a single driver which is of a huge size. We split the work so that one guy has to drive only a certain amount of load, and we connect driver chains where this guy 1, 2, 3, where 3 W by L is greater than W by L of 2, where 2's W by L is greater than W by L of 1, and hence the capacitance is uniformly distributed, and hence there is not a lot of pressure on one guy to drive the entire load, and hence I assure that my circuit does not become very slow. How many such inverters and all that we can connect, that depends on the number of stages through logical effort, which we are not getting into right now. Hope you have followed this. Stay tuned for further clips, and thank you very much.